In blackness, a second image appears, drawn in warmth, sharp against the cooler ground. A ghost of heat guides the coil toward a single living point in grass. The hunter is a snake, patient, body aligned to an unseen glowing outline. This is snake infrared vision, built from paired pits between each eye and nostril. Each pit samples minute temperature contrasts ahead and sketches a crude thermal map of space. A thin, innervated membrane faces a cooled air chamber, boosting sensitivity without heavy energy cost. How do snakes see heat when light fails and prey holds still beneath leaves? The pits resolve small differences across the forward field, emphasizing warm contours over the cooler background. Sensitivity shifts with ambient temperature and wind, which can blur edges or carry heat scent away. Researchers frame pit viper heat sensing with 3 complementary mechanisms that explain reliable aim. One view treats the pit as a pinhole imager, organizing heat across the membrane into spatial patterns. Another emphasizes ion channels, transducing tiny temperature jumps, while brain circuits sharpen boundaries and suppress noise. Neural integration overlays thermal and visual signals in the midbrain's map of space for action. When light returns, the 2 images fuse, adding edges, depth, and motion for a firmer steering cue. When eyes are covered, thermal alone still drives targeting, preserving direction and range in darkness. Strike accuracy remains high even in darkness or under careful blindfolds during controlled tests. The head swings to align the hottest centroid with the jaws before muscles release stored power. Timing follows the target's movement, predicting the path a fraction ahead to place fangs precisely. Wind and self-warming threaten clarity, but behavior compensates before commitment to a strike. Brief head scans sample from multiple angles, averaging out drafts and confirming the thermal outline before attack. The mouth opens only after the map stabilizes, reducing misses that waste venom and reveal position. Not only vipers use this channel when nights cool and prey radiates more strongly into air. Some boas and pythons possess analogous heat pits along their lips, covering wider arcs around the face. Multiple pairs trade spatial detail for breadth, aiding ambushes from branches and ground tangles alike. Field engineers borrow these principles to guide robots through smoke and darkness in collapsed buildings. Passive thermal sensors locate warm bodies, while software fuses camera edges and temperature gradients into stable targets. Simple rules prioritize nearby, hotter shapes, conserving battery while navigating drafts and flickering heat sources. In rattlesnake hunting, the fused map sets the head, then the strike tracks the moving hotspot. The body anchors against ground, coils release, and trajectory closes before the prey completes its next step. Even with shallow cover, a few degrees of contrast prove enough to pull aim true. The design reveals a partnership between peripheral physics and central computation, tuned for survival. A lightweight sensor harvests environmental order. The brain overlays streams and chooses a single actionable point. Success comes from restraint. Sample, confirm, then move when the ghost becomes geometry and geometry becomes dinner. Precision here is not magic. It is measurement under tight constraints with clear payoffs. The organ reads energy flow, the brain writes a map, and behavior executes a timed answer. In darkness, heat becomes handwriting, and these heat-sensing predators read every line.